Okay, let's begin. Welcome everyone to this second week of numerical methods. I'm starting to get to know your faces, bumping some of you in the department. I appreciate your saying hi, and I'm saying hi too. So thank you for that. Couple of announcements first. These red papers, they're unrelated to numerical methods. So you're welcome to recycle them, take them home, or leave them here. They're from a previous class. There are not your groups. Your groups will be formed this week. You get to self-select and name your group the way you like. Okay. That being said, if you still have that name tag of yours, please put it up. I still want to remember your names. I want to make that effort. Okay. Keep it in your backpack or your bag, and so you can use it every time. I sent out an announcement about Exam 0. Please make sure you read that. It has a lot of details in it. If you have questions, please send me a message through Canvas. Okay. And I wanted to share with you what you see on the Canvas front page. So this is what you will see when you log into Canvas. Okay. When I say please refer to the syllabus, I do not mean this syllabus here. This one is kind of auto-populated. Somehow I frankly don't know how to even use that. So just go to the home page. I put everything. It's a brain dump over there. Everything is put over there. But do read it. Do read it, please, because it will have regular updates. So there's the one-page syllabus over here. You click on that. You can see the one-page syllabus. The full syllabus, and a few of you have asked about this, the full syllabus contains, it's a live document, it's a Google Doc. It's longer than the iTunes user agreement, but it does the job. Okay, I don't expect you to read all of it, of course, but it has a lot of resources for like Python, AI use policy, et cetera, et cetera. But at the end, there's this beautiful table showing the tentative schedule. Now, on the front page, I will go ahead and start filling the table here. That's the actual table of what we're doing. This is the tentative table of what we plan on doing. So today we are here. This is week number 2 on Tuesday. All right? So this is what we plan on covering. We expect that homework 1 is due on Thursday, and homework 2 will be assigned on Thursday, and so on. Okay? So this table is super useful. I try to stick to this schedule as best as I can. You see exam 1, February 22nd, tentatively, and then you got your spring break, then exam 2 on March, etc. So all the way to the end. Okay? Many of you have asked for this. It's easier for me to put it in the Google Doc because I link it to a table from Google Sheets, and it automatically updates everything. So please refer to that if you want to look at the schedule. And again, on the front page, once we finish with the lecture, like today, we plan on talking on approximate error, some Python indexing and slicing, etc. And then I'll post the YouTube lecture over here. Okay? These are the previous YouTube lectures, 2021, 2020, 22, 23, and so on. I don't go back further in time because those are kind of obsolete right now. And at the end, there is information about exam 0, right? Some study guides, a refresher for you, and the visual syllabus. Okay, so I hope this clarifies everything. The front page of Canvas, it's not that long to read, frankly. That's your go-to place to see. I will post information on exam 1, on exam 2. I'll update the lecture, the PDFs, etc. One more thing I'd like to mention is that the PDFs of the lectures also are not hosted on Canvas. They are hosted on my Google Drive. The reason being, when I update the slides, say I'm discussing a topic with you and you catch a typo in my slides or there's an error, I go and update it. I update the PDF. I don't have to go ahead and upload the file and delete it. Everything stays in the same location, but this links to a Google Drive with the PDF in it, and you get to see the most updated stuff. Like, for example, I updated the lecture for today, and you should always grab the most recent version. All right, I think I mentioned that in an announcement last week. Okay? All right, so I hope this clarifies at least this issue. Okay. Now we can proceed with our discussion, I'd like to remind you what we covered last time before we had to leave. We were asked to compute the relative approximate error for this toy problem, computing the first derivative using the forward Euler method. We did it by hand, and then the question was to do it in Python. Okay, and that was an activity that we were going to do together. Okay, so please grab your Jupyter notebooks. If you have it installed locally, CHPC, take a minute. Pick up where we left off last time. I still have that notebook up and running. And so to remind you, we wanted to create a Python routine that computes the relative approximate error when approximating the derivative using the forward Euler formula for the function 2e to the half x at x equal 3, and using these values of h, 8, 4, 2, 1, 0.5, and so on. So we're going to compute the derivative for 8, the derivative for 4, for 2, etc. And then we'll take the difference between the two, divide by the more accurate value, right? And then that will give us the error. Now, the reason I do this exercise, this is a warm-up exercise in Python. If you follow with me, this will cover about 50% of the things that you will need to be doing in Python as we move on. So please try to pay attention, and we'll take a break at some point. Okay? So I'm going to switch to my notebook. And again, we'll do this with you here in class. So all good? All right, do you have this on your computer? Okay, you should try to follow with me exactly as I'm doing. And you might find this like inefficient. That's OK. I'm doing this on purpose to make a point. Okay? So like I said last time, I'm not expecting Shakespearean level coding from you in this class. Okay? The bar that we need to cross is for you to become comfortable with using a programming language to solve a problem. There will be instances where an improper use, an inefficient use of the programming language is going to take more time than would normally do. So I'm hoping as we go along, you pick up some of the tricks that I will share with you. So this brute force approach that I'm taking here to demonstrate this problem is effectively using Python as a calculator, just a very fancy, expensive calculator, not using the full power of vectorization and for loops and if statements and so on that are brought about by programming languages. All right, so let me bring the slides to over here as well. All right, so we had these h values. I'd like to compute the relative approximate error. We need to compute the derivative for each one of those h values, and then take successive differences between them to evaluate the approximate error. If you remember, the formula for the approximate error was the higher accuracy approximation minus the lower accuracy one over the higher accuracy one. And we know for this derivative that the smaller the h, the more the accuracy. That's kind of, we trust the math from that. So I know from theory that the derivative, this formula at 4, is more accurate than the formula at 8. So I'm going to take 4 as my more accurate one, minus less accurate over more accurate, and so on. So the simplest way of doing this is, again, the brute force approach. We're going to evaluate the derivative at each one of those values. So start computing approximations, h equal 8. I'm going to call the derivative df. That's from df by dx. df, do you have a question? Oh, should be 3. Thank you. It's just for illustration purposes, OK? So 0.3, 0.5 doesn't matter, shouldn't matter. All right. OK, so great. So this is the derivative at h equal 8. I'm just going to copy and paste, and we'll go to the h equal 4. OK, so df at 4 is, again, same formula, right? It's the forward Euler, f at x plus h minus f at x over h. Now I change h over here. And then I'm going to print df4. Right? So now I can define the first error. Let me call it E1. And that will be the absolute value. I'm going to call numpy.absolute.abs. So just use the numpy absolute value. And I will do df4 minus df8. And I put everything in absolute values over df4. Agreed? So that's the more accurate minus less accurate over the more accurate. We can't compute an error for df8 because there's no less accurate formula for it, at least in our setup here. There's no less accurate value that we have. And if you go ahead and print E1, you will get that first error. So I'm going to comment out df4. In the comment, you put this sharp symbol. Still use the sharp symbol from music, like F sharp, G sharp, right? All right. So now you see we can repeat the same thing over and over again. And I want it to be painful. Okay? So you want to copy, paste, just to prove a point. For h equal 2, we have df2. And then our second error is E2. It should be df2 minus df4 over df2. Because in this case, df2 is the more accurate one, right? It uses the smaller value of h. Okay? And then print E2. Okay, great. Now we expect that the error to decrease, correct? As we decrease h, we expect the error to decrease. Great. The first error was 3.19. The second error was 0.86. Very good. So we're on the right track. I'll continue with a couple of values. For h equal 1, that will be, call it df1. And then we'll have df1 minus df2 over df1. And I'll call this E3. E3. Okay, the error continues on decreasing. And again, the next value was 0.5. And we will have df 0.5. So you cannot type, for a variable name, you cannot have a decimal point in it. So I would just do 0.5. Okay? So df0.5 is that formula. So, and then the relative approximate error, df0.5 minus df1 over df0.5. Now let's call that E4. E4. Indeed, the error continues on decreasing. Okay? Are we all in sync? Great. And we continue for the other values of h. I think you get the point. And you also get the point that this is repetitive. The only thing we're changing is the value of h. Right? We're changing some variable names, but that doesn't matter. We're changing the value of h over and over again. Now, if I were to ask you to do this for 1,000 values of h, and we do it this way, that's going to be ridiculous, right? Because we are misusing Python. We are using it as a glorified calculator. For small problems, be my guest, do this, that's fine. Okay, great, just do it, get the answer, okay, and move on with your life. But for a real problem, for most cases, you're going to be dealing with large data sets, maybe 100,000 values. You can't do that with 100,000 values. Copy, paste, change. We need a mechanism to effectively be able to work on an entire array, for example, and use for loops and things like that. All right, so let's go ahead and do that. First, let me introduce to you a couple of concepts in Python. And again, I know some of you have seen this already. It's good to reinforce what you've seen. And for those who haven't seen it, this will be a good introduction for that. All right. So I want to introduce you to Python array slicing. which is a great mechanism to operate on arrays. If you could imagine that if we had that entire array of h values, and we could call on that entire array f of x plus h, and return an array of f of x plus h's, we would do the whole thing in one line. Turns out that Python was designed for that kind of stuff, exactly for that, right? An array in Python can be thought of as a sequence of buckets in memory that contain values. This is an array, A. It has these values, just some random values I put in, 5.4, 7.2, and so on. For an array to be beneficial, you need to access values in it. The standard way of accessing an array is called indexing. And we can operate on Python arrays in two ways. Forward indexing, where the first element has an integer index of 0, the second element has an integer index of 1, and so on all the way to the end. So this array, how many elements does it have? It has 7. They're indexed from 0 to 6. Okay? Unlike MATLAB indexing, if some of you have used MATLAB, it's typically 1 base. The first element is index 1. Python uses 0 indexing. It's just a convention, doesn't matter. But keep that in mind. The first entry in an array is located at index 0. Okay? Second entry is at index 1, and so on. Now, how do you access the value that is contained at any of those indices? You just use the bracket notation. Okay? You say A, open bracket, put the index here, that integer index, and it will automatically, if you say A0, it will return the value of 5.4. Okay? You can also change the value at A0 by putting your own value in it. Okay? For example, to access the fourth element, which is at index 3, you just say go A3. All right. Now, what is cool about Python is that you can index backwards, right? And you use negative indexing to index backwards. Why is this super useful? What if I give you an array, and I don't give you the size of that array, and I tell you, get me the last element? What would you do? You need to count the number of elements on the array. You could say, hey, first give me the length of the array. Length of array gives you like 500. And then you go A 500 gives you that last entry. With reverse indexing, you don't need to do that. You can just say A minus 1, and it gives you the last index. A minus 2, it gives you the second from last index. All right? So here are examples. A minus 1 is 0.3. A minus 5 is 33, because we've gone minus 1, minus 2, minus 3, minus 4, minus 5. Now note, forward indexing is 0-based. Reverse indexing is 1-based. The first entry from the end is at index minus 1. Okay? That's great. This is how we access an array. Now here's what's powerful about Python. So I'll introduce this before we go back to the notebook. You can also get subsets of an array. We call those views or windows, right? And this is called slicing. And just bear with me for a minute, and you'll see how this is going to be very useful when we go and do the derivatives. Okay? The notation is simple. To access a subset of an array or a slice of it, you use these semicolons, and you say A, start, semicolon, stop. And it will give you a view of the array that contains the value A at the starting point, A at start plus 1, all the way to stop minus 1. So it's not including that last entry. It's like an open interval. Okay? Note that the element at the second index is not included in the view. Right? It's an open index. So here's an example. If I go A, 0 to 2, it's going to give me the element A at 0 and then A at 1. Right? So if you call this, it gives you this view of the array, this subset of the array. You will see in a minute that this is going to be very useful. Now here's a little note. This might not apply right now. If view is not a copy of the array, it's a reference. So let's say you create a view, you put it in a variable, which is going to be an array type variable, and then you go and modify that, it's going to modify the original array. Okay, you're not duplicating the original array, you're just getting a pointer to it, a reference to it. You modify the view, you modify the original array too. So that could get you in trouble, right? Now there are some really cool things that you could do with this slicing. For example, if you don't include a value on the right-hand side of these semicolons, then it goes all the way to the end. So A3, semicolon nothing, is going to start at A3, which is 21.2, and gives you all the remaining entries. This is cool because now I don't have to worry about what is the size of the array and what is the last entry and et cetera, et cetera. And you can also use negative indexing, right? Remember, when you put a stop point, it's going to keep an open interval here. So this one is going to give you from entry 3, which is 21.2, all the way to entry at index -2, because it is open at that stopping point. Okay? And on the slides, I have a summary of kind of how to use this slicing approach. Okay? Let's do it together. You can spend time later to absorb this. All right, so how can we use this to our advantage? Let's go to Python. Okay, so a better approach. Okay. In this better approach, again, if I had time, I would explain what I'm doing. It's a good practice to do that. I would say in this better approach, we are going to use the power of arrays and indexing in Python to solve that problem that we solved with the brute force approach. We're going to try to use arrays to solve that problem. Now, one more thing. Python operates on a single value number, like a scalar. We call that a scalar, but also can operate on a full array. So let me give you an example. Suppose I want to calculate exponential of 1, exponential of 2, exponential of 3, exponential of 4, exponential of 5, whatever, right? Like 3, 4, 5 values. You could do np.exp.exp1, and then np.exp2, and so on, right? Or you can declare an array. This is how you declare an NumPy array. Now, np.array, you open parentheses and then open square brackets, and put the values you want to compute. Okay. Now Python, because this is a NumPy array, anything I use from NumPy is going to operate on that array element-wise. So if I call the exponential function on x, it does return an array, and that array contains the exponential of each one of those values in that array. The first one is the number e, 2.718, etc., right? The second one is e squared. The third one is e cubed, e to the fourth, and e to the fifth. This is super powerful, right? Because now I can use that to compute f of x plus h. Remember, h was an array. If I put h as an array, I can get f of x plus h in one shot. I don't have to change h every time. Make sense? Okay, let's see it in the works. All right. So I'm going to redefine my problem. X is 3.0. I'm going to do my h values. Where were they? The h values were here. 8, 4, 2, 1, all the way to 0. Okay, so h values is an NumPy array. And we start with 8, 4, 2, 0.5, 0.25. Okay, 0.0625, right? Sorry, 0.125. Can't even divide. All right. Now, if I do np.exp x plus h, what do you think it's going to do? So first, what is x plus h? Remember what I said last time. When in doubt, print it out. So just print x plus h. Oops, h values, sorry. H values. What did it do? It added 3 to each one of those entries. So I didn't have to do any for loops or access each entry at a time. In one shot, I was able to create a new array augmented by the value of 3. You're just simply adding 3 to every entry in that array of h values. Now, the same applies when I do np.exponential of x plus h values. It just computes it. It just computes f of x plus h. Okay? Now, specifically, what was my f? It was 2 times np e to the 0.5. Okay? So this is what I want to compute here. Okay? I want to compute the total numerical error. The relative approximate error. And I'm going to call those df values. And print df values. So this is what I'm doing here. I'm taking that formula, the forward Euler, that says f of x plus h. I'm going to call it h values. I keep changing. Should be h values. Okay. So f of x plus h minus f of x over h, it's going to do it one by one. Internally, it is actually doing a for loop. It's going through each entry in h values, adding to it x, and doing that calculation. Okay, so let's run this and see what happens. Indeed, it returned an array. What does this array contain? Think with me. The derivatives, right? The derivatives at x equals 3.0, using h equal 8, using h equal 4, derivative using h equal 2, and so on, all the way to that last value. This is the value of the derivative at h equals 0.0625, using h equals 0.0625. What took us 7 lines of code or whatever, just do this in 2 lines. But you have to keep track of what you're doing. The paradigm shift in your thinking is now you have to think in terms of arrays that contain numbers. And what does each number mean? These are just simply the derivatives. Okay? So now that we have the derivatives, we're very close to computing the errors. Okay? So what would you suggest we do? Take a minute, think about it. So I have now an array of the derivatives at the different h values. And I want to compute a relative approximate error for each one of those h values. Clearly, there's no error defined at the first h value, just like we did in by hand. But over here, we can define an error between this value and that value, this value and that value, and so on. So for those of you who know some Python, what would you suggest we do? Do a for loop. Yeah, for loop would suffice. Okay. You've heard of for loops. Anybody disagrees? It is a solution. Okay, let's go ahead and do it. So what your colleague is suggesting is we loop over the entries in this array, or we loop over some number of items and take this value minus that value, and then this value minus that value, and then this value minus that value. We divide by the more approximate value, and so on. So we need a counter. Okay, we need a counter. That counter is going to be the number of errors that we can compute. So how many errors can we compute here? We can compute 1 error between these two, 2 errors, 3 errors, 4 errors, 5 errors, 6 errors, 7 errors. Or the total size of this array minus 1, right? Because this array has 8 entries, 1, 2, 3, 4, 5, 6, 7, 8, right? because we can't compute an error for the first value, right? There's no worse approximation for that. Okay? How bad am I losing you here? Okay, so let's do the for loop. For my counter, just going to go get the length of this array. So if you call this thing called len, it gives you the length or the size of an array. Now note, as we're going through this exercise, I'm trying to teach you some programming in context. I'm introducing a value, just throwing it at you, like just use it as is. Okay? So you learned the word print, you learned an np.array, right? You learned len. Now you learned how to create an exponential function. Okay? You learned np.absolute. That's frankly a lot of what you will be using later. All right. So now I want the length of this array, df values or h values. It doesn't matter. It's the same length. And if you're in doubt, print it. Okay? Print n. All right. It has the value of 8. Great. Now I need a loop. I need to do a loop over a counter. How can I create a counter in Python? If you've seen it, do you remember? Integer equal to 0, but then I need a range, right? Okay, so in Python, there's something called the range function, okay, that allows you to create a sequence of numbers from beginning to an end, right? Let me show you the syntax first, and then you'll be amazed at it. So if you type this for I in range from 0 to 10, print I, look what it does. It's just a counter. It counts things. The range function starts counting from the first number that you give it and ends at the last number minus 1. Again, it's an open interval. Why? Because the developer who created the range function wanted it to be like that. There are other counters that include the last entry. Just make sure you use it right. And again, when in doubt, print it out to see what it's going. Just come up with a little toy example. I forget what the range function does sometimes. So I just open up a new cell, type in something like this, and print it. Right, so you can change your range. You can start from 2 to 10, and it will start from 2, goes to 9, right? Okay? Okay, great. So now I can go for, now what did I do here? This is the standard Python loop. It automatically creates a counter called I. So it's counting. I, the value of I here is 2, value of 3, goes over and over again. Right? So I automatically created a counter called I in the range from 2 to 10. And the for loop, that's how you do a for loop in Python. That's the simplest for loop you can do in Python. We'll learn more advanced ways of doing for loops later. But for now, this should suffice. Okay? So now I want my counter for I in range, right? Going from 0, but I need to go to n minus 1 now. Remember, because I have n minus 1 errors that I'm computing over there. Okay? I have n minus 1 errors that I'm computing in that array. So I need to go from 0 to n minus 1. Then what do? I compute an error simply by saying, this is the np.absolute, just like we did a little bit above here when we took this difference, right? The definition of the error. So np.absolute, df values of I plus 1 minus df values at I over df values at I plus 1. So think of it this way. You enter the for loop, I is going to start taking on values in this range, 0, 1, 2, 3, 7, whatever, right? Forget about I. You enter the loop, you have the first value of I. I is 0. Okay? To compute an error from that array of derivative values, I need the value at the more accurate version, which is at 1, that's 4, that's the value at 4, right? Minus the value at the lower approximation, which is the value at 8. So that's I plus 1 minus I over the more accurate value, which is located at I plus 1. So what this loop is going to do is going to take 14 minus 60 over 14, and then 7 minus 14 over 7, and then 5.8 minus 7.7, and so on. Okay. You don't believe me? Let's print it. When in doubt. Okay. All right, so let's do it. Print df values at I plus 1, and then df values at I. Okay? Then you'll see, let me format it a little bit. I'm going to print I, and then I'm going to add semicolon. Okay. This is what it's doing, the loop. At I equals 0, it's grabbing the value at 1 minus the value at 0, taking the difference, dividing by the value at 0, and so on. Okay? I can't read your minds. Okay? If something is confusing, not clear, just speak up. Yeah?
Can you just say one more time when you're indexing, like slicing a number, right? What are the two values you put in the...
So we haven't gotten the slicing yet. The next step is going to be slicing, which is the better solution than even this one. Okay? We haven't gotten to slicing yet. Okay? But I'll cover that in a second. But the range, so it's similar to the slicing. It takes the first point, but stops at the last point minus 1, always. Right? So think about it here at index at I equals 6, is going to access df values at 6 plus 1, which is 7, which is the last index in that df values array. So now if I print the error, I'm going to go ahead and print the error so that, okay, and then print E, the error. I'm going to say error equal. All right, look at that. Now if we go to our previous approach, we had 3.19, 0.85, 0.32, 0.14. Look at that, 3.19, 0.85, 0.32, 0.14, and so on. They're the same. And that's what you need to do when you're working a problem out. You do it by hand for a couple of values. Then you double check that your implementation makes sense. Or you do it a few times with the brute force approach, if you trust that better than a for loop or something more elaborate. Now, this will work regardless of h values. I could have 1,000 values in h values, and it will just work. It's just going to do it. How can I have 1,000 values in h values? You can either input them by hand, read them from an input file, or create a linear space, for example. We'll talk about linear spaces later. OK. All right, so now I want to get to an even better way of doing this. Now this is, again, for a small problem like this is great. Just do it. You want to do it like that, be my guest. I'm not judging you on your coding skills. Okay? This is a better approach, but if you want to be further sophisticated, let's do an even better one. Using slicing. Okay. So this is where I typically lose most people, but I want to go back to the array of df values. I'm going to zoom in a little bit here. Okay. So if you think about what we're doing here, we want to take the difference between 14, 7, 5.8, 5.0, 4.7, 4.6, 4.5, and 60, 14, 7, 5, 5, 4.7, and 4.6. We want to take the difference between two arrays, okay, that are not that full size of an array. So if there was a way where I could create two arrays, one that contains the I plus 1 values and one that contains the I values, then I can take their difference and evaluate the error in one shot. Let's see how this could work. And in many ways, this is cleaner. So if I were to take df values and use the slicing technology, if we go from, if you remember the slicing, it has a start and stopping value. If we go from 0 to the end, it just returns that same df value. So let me print df values here as a reference. Okay, this is the true full array of df values. Okay. So now play around with this, with slicing. I'm starting from index 0, so that's the first entry, 60.05, right? And if I go to -1, it's going to give me one less entry here, right? Because it is not going to include this, it's going to include this guy, right? So that's a subset of that array. Agreed? Make sense? So I go to the last entry, -1, right? Okay, so check this out. I said that I wanted to take the difference. I wanted two arrays, one that contains 60, 14, 7, 5, etc., all the way to here, and another array that contains the values to the right. So I can create those with slicing. Okay, look at this. If I do df values and then start from 1 to the end, I've created two arrays, both of the same size. Just visually, you can inspect that. But one of them contains the values to the left. One of them contains the values to the right. And notice this. The first entry, that's going to be 14 minus 60, which is the error at h equal 4. The second one is 7 minus 14, and then 5 minus 7, 5.09 minus 5.08, and so on. So if I take the difference between these two arrays, that will give me f of x plus h minus f of x. Sorry, it will give me the error between the derivative at the most current, the higher approximation minus the lower approximation over the higher approximation. Okay, so let me show you. If I do df values, okay, I'm going to keep this here. Now say errors is equal p dot absolute value. So I'm going to create, just open up absolute value, and I do df values from 0 to -1, or let's do it this the right way. Higher approximation minus lower approximation, and you can ditch the 0 if you want here. Okay. And let's divide by the higher approximation, df values, which is contained in that other array, and print errors. So if we did this right, we should get these answers here, right? 3.19, 0.85. Let's see. Look at that. 3.19, 0.85, 0.32, exactly the errors that we expected. Yes, Kayla. Yeah. So the numbers to the right are the numbers that contain the higher order approximation. Okay, and the numbers to the left are the numbers that contain the lower order approximations. In other words, when I take the difference, so this array contains all the derivative values. Our errors are going to be defined as the difference between every two consecutive numbers. So in other words, if you were to stand between these two numbers here, the value to the right minus the value to the left gives you the error. And then if you stand between these two numbers, in the middle. The value to the right minus the value to the left gives you that error. That's what I'm referring by that. So then if you collect all the values to the right, they're going to be 14, 7, 5, etc. The values to the left are going to be 60 all the way to this one. Make sense? So the error on the last one, this is the right value, this is the left value. Okay, so this one belongs with the left array, which is this guy, and this one belongs with the right array, which is this other one. Okay? Now, this is doing a for loop internally. But Python is so much better at the for loop because it has a compiled for loop, not an interpreted for loop. That lingo means it's just faster. It's just a faster for loop because it's using actual machine language doing it. Now, this is a silly example here. But when you're working with 100 million values, this will be the difference between night and day. Okay? So when I use this built-in procedure, Python is optimized to do this stuff, even better than the for loop that I typed in Python, because it was built with this stuff in mind. These are called vectorized operations. It simply means you're doing one element at a time. It's taking every element in an array, subtracting from the corresponding element in the other array, and doing them point by element. So internally, Python is looping over these arrays and taking value at 0 minus value at 0 over value at 0, value at 1 minus value at 1, and so on and so forth. So now compare that to our for loop and brute force approach. It was literally a couple of lines of code, right? Declare h values, compute df values, and take the difference. 3 lines of code. You do this whole problem. Again, I'm not expecting you to write Shakespearean style code. If you want to, great. If you want to learn it, push yourself, that's great. You can do any one of those tiers, right? In some problems, it's going to be really inefficient, nearly impossible to do the brute force approach, because I will ask you to do a problem with 10,000 equations. You're going to be like, yeah, you have to do a for loop. There's no way around it. You can do it by hand to demonstrate to yourself what the answer looks like for a few equations, like do it for 5 or 10 equations, right? But for anything beyond that, you have to start thinking this way. Okay? So there you go. Now we've covered nearly, I promise, almost like 50% of the things that we are going to do in Python. Again, programming, there's 2 things, the idea of what you want to do and the syntax. Okay? The idea is what matters. The syntax is something you can Google and learn, but the idea is more important. Now, there's some augmentation of ideas here, like, yeah, let's think of arrays and subtract arrays from each other, right? It doesn't take much to make that jump, okay? All right, let's do one more thing, and you'll take a break. Okay. Okay, we go through this. All right, great. So now, notice that we only used x equals 3 and we hard-coded our function, right? But I want to now compute the derivative for an arbitrary function, for any function, not just 2.0 to e to the 0.5x. Okay? Do you think we can do that? Absolutely. Yeah, if we can't do that, bad Python. We will leave Python and go to another language. Because that's the whole point of programming, is to template everything, do it in a modular way. We can throw anything at it, and it will work, right? Imagine they designed ChatGPT to only do, like, I don't know, one specific type of thought, right? It cannot, it would be silly, right? It would be useless. Or Google would only search for movies. That's it. Like everything you learn about from Google comes from movies, nothing else. That would be kind of silly, right? Okay, so now repeat the previous coding activity, but do it so that one can use an arbitrary function f of x and arbitrary value x. In other words, write a subroutine that computes the first derivative using forward Euler for any function f of x at any value x. So now we're going to do it for any function. For any function. All right. So I want to be able to, so let's think it through. I know I don't have all of these pseudocodes written on the slides because I don't want to prescribe the recipe in my head. I want to think about it with you here and make mistakes in the thought process and or do it better every year. So here's the objective. We want a function. Let's call them routines from now on. So let's reserve the word function for a math function like exponential, sine, cosine. And let's call the function in Python, let's call them routines. So that you know, oh, it's a routine that means, he means coding when he says routine, okay? So when I say routine, it means a Python piece of code, okay? So we want to create a Python routine that computes the forward Euler derivative, the rise over run, for any function f, any math function f, at any value x. What's missing? H, right? The run, that thing in the denominator. So if we were to conceptualize this, I want to create a Python routine that computes the forward Euler derivative for any function f at any point x. Okay, so suppose we call it forward Euler. It needs to take a function f, a point x, but it also needs an h value. Okay? So that's what I want my routine to look like. The beauty of Python is that most of the time your routine looks exactly what you dreamt about. All right? So the syntax to define a Python routine is called def or define. Once you give def, see how Python changed the color? Python is like, yes, give it to me. Give me that name of the subroutine, okay? It's waiting for a subroutine name. Let's call it forward Euler. Now, any routine in Python, so that it's a proper routine, it needs parentheses. Because a routine is expected to have inputs to it, or argument. Just like you say sine of x, right? Or in 2D, sine of xy. Right? Those are the arguments of the math function. The same thing for the routine. It needs input values. It needs arguments. In our case, our argument is some function f. Let's call it some function. Okay? And an x value and an h value. Now, I'm being very explicit here in my naming to elaborate the naming conventions, okay, and what those mean. In practice, you might just call this f, comma x, comma h. Okay? But I'm trying to be as descriptive as possible. Okay, so this is what Python expects. The word def, the name of your subroutine, parentheses, and whatever arguments you want to give it. What are those arguments? Python doesn't care. They're just inputs. They could be arrays. They could be single values. They could be the names of functions. They could be tomatoes. Now, inside the subroutine, if you misuse a type or mix it with another type, you multiply a tomato with an array, it's going to be an array of tomatoes, or you add potatoes and tomatoes, it's not going to add up. It will throw an error. But at least for now, it doesn't care. You close the parentheses, then you need to follow this with a semicolon. Okay? So now we define the subroutine or the routine, the Python routine. Now, the first thing I do whenever I create a subroutine or a Python routine, I immediately type return result so that I don't forget to return a value. Because if you think of a routine as a machinery that takes a bunch of things and produces something or many other things, you need to return something. Otherwise, it's useless, right? Unless it's operating in reference. But for now, you need to return something. So I always return result. What is result? It's whatever I'm going to compute. I always call it result so that I know this is my result. This is my answer. I'm returning my answer. Okay, what is my answer here? Result is equal to some function at x value plus h value minus that same function, same function at x. Now I need to divide by the h value. Is that weird? It's a routine that calculates the derivative according to the forward Euler formula. Its inputs are some function, the name of a function, could be exponential sign or whatever your own function you've created. It takes an x value and an h value. Seems too good to be true. It is true. It is so good to be true. That's why we love Python. It is so good. Okay, so let's try it out. Okay, forward Euler. And I want to give it the exponential value. I just say np.exp. That's the function name. Sorry, the function name. Some function, numpy.exp. X value, I want to say 3. And h value, I want to say 0.5. It computed something, right? Now, if I want to do it by hand, that will be np.exp at 3 plus 0.5 minus np.exp at 3, right? Over 0.5. Let me add parentheses. So those should give the same answer. Look at that, right? Makes sense. Now, you need to do this. When you create a routine, try it out. Make sure that it works as you expect. So now, the sky is the limit. I can use this forward Euler instead of the df values that we did over there and doing it by hand. All I need to do now is define a new function, which is 2e to the 0.5x. Now, that doesn't exist in Python proper. So I need to create a routine for that function. Okay, so I'm going to do def my function. And I'm going to return result. Result is equal to 2.0 times np.exp of 0.5 times x. It's complete because there's no unknowns here. The constants are constants. They're known. The function value x comes from the user, and it's used over here, and it returns a value. Okay, so if I declare this my function, now I can do forward Euler, and I can tell it, hey, apply the forward Euler on my function at the x value of 3.0, okay, and at some h values. Look at that. Did the whole thing that we did manually. Yeah. Where? Oh, I apologize. Yes, sorry. Because I chose the same 3 here. Okay, we just got lucky. Yeah, good catch. Thank you. It would have failed if we restarted the kernel or chose a different value. Thank you for that. Okay. Yeah. Now the best thing is I can try this for any other function. Def, my other function. I'm really good with names. Very, very good. Very creative. Result, let's say, is equal 3.0 times np.sine x times np.cosine x. And return result. And you can do the same thing now. You do forward Euler. My other function. Oh, what happened? Look at, I didn't even type this. Look. If I type O and press tab, it auto-completes things. So for variables that already exist in your code, you can press tab. It will autocomplete the name of that variable. Start typing the first few letters, and press tab. It autocompletes it. And I want to do this at like 2.0 and h values. And it does that for you. So remember, this is a course on numerical methods, not programming, not Python. But to do any serious numerical methods, you need to do programming. And we love Python, and it's free. And so we're going to try to balance that, right? Now I want to get back to the theory and what is important, because the programming is only a means to an end. What you as engineers are going to be dealing with are the concepts presented here. Yet you have to use tools to implement them, but it's the concept that differentiates you from just programming blindly, okay, being able to understand what you're doing. So here's one question. Okay, we introduced the concept of approximate numerical error. We did this kind of silly little example about f prime. Frankly, like who cares about that? That's, it's just a toy problem. So one use of approximate numerical error, and trust me, there's a lot of uses for it, especially in my research area, computational fluid dynamics. But one use that you can relate to immediately is the Taylor series, and specifically to stop a Taylor series from taking over the world. So what I mean by that, this is an image created with GPT before coming here, because the Taylor series is an infinite series, right? Remember last time I said we cannot truly compute these complex transcendental functions like e to the x or log x or square root of x, because at the end of it, at the bottom of it, any calculation is going to rely on additions. And you need to express things in terms of additions and multiplications, right? That's why Taylor series is powerful, because we can take a function like the exponential or the logarithm, express it in terms of things we can actually calculate, like x squared, x cubed, and so on, and then just use standard computational algebra to compute an approximation to that function. Now, the Taylor series, the problem with it is that it is infinite. And if you try to compute all of it, you're going to spend your lifetime adding and multiplying numbers just to get a single value for an approximation for a function. Okay, so that's the idea here. Turns out that the approximate numerical error allows us to stop the Taylor series from taking over the world. So, like I said last time, and you probably know by now, that evaluation of many transcendental and complicated functions relies on Taylor series polynomials. For example, sine x. How do you calculate sine x from a table? No, that table was generated using a bunch of calculations, additions, and multiplications. A standard way of doing it is Taylor series, where you take these complex transcendental functions and you express them as an exact polynomial. We can calculate x, we can calculate x cubed over 6, and so on. Those are easy calculations to do. However, this summation is infinite. So if you were to truly compute sine x, you really can't, because you need to add an infinite number of terms. Same thing for the exponential and many other functions. I bring back the exponential because we've been working with that. So we did a couple of examples by hand. So now, here is how we're going to use the approximate numerical error. Imagine that you want to compute exponential 0.3, again, that example, exponential 0.5 or whatever value, and you start adding terms, okay? Now, for each term you add, you evaluate the error between the current term and the previous term. If you remember that example we did last time where we created that table and showed the error, and eventually the error stops at a point. We can't improve anymore. All the values, they stop at a point. So let me pull that back. If you go to my previous slides over here, if you remember this slide, where we computed the Taylor series for the exponential of 0.3, And we started adding terms, 1 term, 2 terms, 3 terms, and so on. And notice that the value eventually stops from changing. So if you are doing this for an infinite number of terms, you're just adding and doing nothing, not improving at all, right? So this is where the approximate numerical error comes in handy, where we can track the approximate error committed between the different terms and say we're going to stop when that approximate error is less than 1% or less than 5% and so on. Okay, so that's what this problem is about. That's what this problem is about. Write a Python code that uses the Taylor series to evaluate the exponential function down to an error, also called tolerance, of 1%. So in other words, we will keep adding terms until the relative approximate error between 2 consecutive terms is 1% or less. So once we hit 1% or less, we stop. This is great because that tells us, look, we've done our best. 1% is an acceptable error that we choose, right? You can keep doing it for an error of 0.1%, but at least it's a stopping criterion, and it will prevent the Taylor series from taking over your computer and the world. Okay, so I created a Jupyter notebook for you already, but it has gaps in it. Because I want you to spend a minute now. You go ahead and download this notebook from the errors module in Canvas and load it up in your Jupyter notebook on CHPC or your local distribution. It has some text in it and discussion. And you are to start going through the code and filling in the gaps. The gaps are shown with question marks. So I'll show you how it looks like. Okay. So this notebook has a lot of details. And I want you to spend a minute going through it. But then at some point, there's going to be these question marks. Okay? I want you to take a moment, spend some time, work as groups. Again, we haven't formed the groups yet, but try to self-select with your neighbor or people around you. Just try to gather next to each other. Maybe one of you drives the coding. And so, and if you don't have, especially if you don't have Jupyter Notebook working for you, so gather up and work with someone else, please. Okay, one of you could have the Jupyter Notebook, and all of you would be thinking and talking about it.